Welcome back to the office. We want to take one last look at an example for trigonometric substitution. So if we look at our notes, we might notice that there are several other examples that are provided. Again, referring back to an example up here, this involves a radical of this particular form, a squared plus u squared, square root of that. And we're looking at such an example right here. So I didn't see the need to repeat such an example, where here we can get in the additional information of integration bounds that we will need to convert. There's also two more examples, and this is partly because some textbooks give this as a special integration formula, as well as this, and then the remaining third scenario. This textbook doesn't do that, and so I don't feel that there's a need to consider these two examples, because we'll actually consider, just in general integrals that involve these square roots. So these are unnecessary examples. I would encourage you to consider them. They would be certainly great to take a look at along with the practice problems. If you're interested in solutions, please let me know and I can post them. But for now, for this video, what we are interested in is exactly this example. So we want to evaluate this integral, but this is a definite integral. It has the integration bounds. So not only do we need to make our substitutions of, we want x to be equal to this, but we also need to then change our integration bounds so we can find that final answer, that numerical value for the integral. The nice thing about this is that, once we make our change of variables, we won't actually have to change it back into x, because our final answer isn't the antiderivative. Our final answer is a number. So we don't have to do all of that changing back. All we have to do is the movement forward, trying to get ourselves into something that we can integrate relatively easily. So this thing, first of all, it doesn't fit in a formula that we have in our formula sheet. These formula sheets give us, these three integrals involving radicals, or in this case, it doesn't have a radical, but a squared plus u squared. So we have the a squared plus u squared, but it's the square root of that. So it clearly does not fit into the formula that we're given right here. So this is part of why we need this trigonometric substitution. All right, so based on our previous conversations, if I go back to these notes and go back several pages, when we have the square root of a squared plus u squared, we want to make the substitution of letting u equal a tangent theta. And that's because of this relationship here, which we manipulated to give us this perfect square. So we can take the square root of a squared plus secant squared theta. That's the goal. So our first thing to do is to let's see here, make our substitution. We want to let u be equal to, sorry, not u, let x be equal to, that should be 3 times the tangent of theta, because 9 is 3 squared. Then dx is equal to, well, the derivative of tangent is secant squared. So this gives us 3 secant squared theta. Let's see, d theta, of course. And once we do that, look at what's going on here. This gives us that the integral is equal to, well, actually, before we do that, we have to change our integration bounds, Change integration bounds. So for x equal to 3, this is going to be 3 is equal to 3 times the tangent of theta based on this equality, We're letting x be 3 times tangent theta. So we divide by 3 to get 1 is equal to tangent theta, and we should recognize that this gives us pi over 4 for theta. For the other integration bound, let's go ahead and write that over here. For x equal to 0, the lower integration bound, that's going to give us 0 is equal to 3 times the tangent of theta. And divide both sides by 3, so left side doesn't change at all. 0 is equal to tangent of theta. And then using the inverse trig functions or a recognition of what we want here, this would be simply equal to 0 is equal to theta. Now we do have some limits on the values that we can use for theta. We have to be a little bit understanding of our right triangles and what makes sense to use. So when we're using a right triangle, we should recognize that our angle should be between 0 and pi. So that is absolutely, sorry, 0 and pi over 2. For the most part, we do allow for angle measures of all the way to negative pi over 2. So negative pi over 2 to pi over 2 should, for the most part, make sense to us. And then the only time that we don't really follow that is when we're talking about secant, because secant is 1 over cosine. So we don't, let's see here. Is there an issue with 0 there? There isn't. Let's see here. There seems to be an issue with the negatives. So what we do is we say theta can be between 0 and pi over 2 or pi and 3 pi over 2. These are some details that if we understand the domains of these functions is right, they should be pretty clear. But for now, right, if you don't want to dig into that, that's absolutely fine. Certainly these values are good for us. But this gives us our change of integration bounds. So our integral becomes the integral from 0 to pi over 4 by the change of integration bounds. X cubed is, and we're looking at 3 times tangent theta cubed divided by, our denominator is the square root of x squared plus 9. So the denominator is square root of, let's see, that would be 3 squared tangent squared theta plus 3 squared. And then dx is, we said that was 3 secant squared theta. 3 secant squared theta. So we've got a bit going on already. All right, so what do we have? All right, let's pull out some constants. 3 cubed is 27. 27 times 3 is 81 times the integral. Let's see here, integral, try that again, 0 to pi over 4, tangent cubed in the numerator. See, we have a secant squared here, but 3 squared times tangent squared plus 3 squared, right? That thing is secant squared. So we have, this is divided by 3 secant theta, and this is 3 secant squared theta. So that looks pretty good. Let's see. 3. Oh, yep. Sorry, I pulled this 3 out. That's where we went there. D theta. Forgot the d theta over here. D theta. There we go. That looks a little bit better. So the secant and the secant will cancel out, and the 3 can be pulled out, or the 1/3 can be pulled out to reduce this to just be 27. So we have a little bit of simplifications already. So this is the 27 times the integral from 0 to pi over 4 of, now I'm going to rewrite this as tangent squared theta times tangent, or we'll call it secant theta, tangent theta. Why am I doing that? Because I'm already recognizing the substitution I need to make to evaluate this trigonometric integral. When the power of tangent is odd, then we go ahead and pull off a factor of tangent. So we have a secant tangent factor, allowing us to use that, let u be secant theta, and du would then be secant theta, tangent theta. So I also have to convert the tangent squareds to secants. So 0 to pi over 4, but tangent squared is, if we refer back, tangent squared is secant squared minus 1. So tangent squared is secant squared theta minus 1 times secant theta tangent theta d theta. And why is this good? This is good because now we can go ahead and let u be equal to secant theta, and then du would be equal to secant theta tangent theta d theta. Now, of course, we're running out of room, but fortunately, this next example, we're not too worried about. We can look at that later if you're interested in that. But using this substitution, this is going to give us 27 times the integral of, oh, but I have to be careful here, right? I need to finish this substitution for u equal to pi over 4. for theta equal to pi over 4, u would be equal to secant of pi over 4. If you don't remember what that is off the top of your head, that's okay. You can find that this is equal to the square root of 2, as long as I haven't done too many mistakes here anyway. And then for theta equal to 0, u would be equal to the secant of 0. And again, as long as I haven't made too many mistakes, we should find that this is equal to 1. So our integration bounds become, this is a little bit interesting, it should be from 1 to square root 2. Excellent. And 0 becomes 1, pi over 4 becomes root 2. And then my secant squared is u squared minus 1. Secant theta tan theta d theta is just du. So this is 1 minus, let's see here, say that the right way. Sorry, u squared minus 1 now. 1 minus u squared. U squared minus 1 du. And hey, look at that. That's not so bad. Now it's just something that is, hey, this is Calc 1. We go ahead, plug and chug essentially, because we know what the integral should be using the power rule. So this is 27 times. Now the notation that you use might be different for different courses. So this we could write as 1/3 times u squared minus u, and then evaluate from 1 to square root 2. Now that's, I think, what I'm familiar with. That might be what many of you are familiar with. I've talked with some of you that have written it that way. It's also acceptable to write this thing in brackets and then put the integration bounds on that bracket. So whatever notation you use is perfectly fine. 1/3 u cubed minus u, evaluate from 1 to square root 2. Either notation is fine. I understand both. You're welcome to use whichever you're familiar with. If you have something other than that, I'm not sure what it would be, but I'm sure I'll be able to make, well, those are the ones that I'm familiar with. I haven't found any others. There is one other that's actually an adaptation of this one, but it's that one. So anyway, I don't think there are any others. But when we evaluate this, of course, this is 27 times evaluation at root 2. So 1/3 root 2, oh, that should be cubed. Root 2 cubed minus root 2. So we take that thing and we subtract the evaluation at 1. 1/3 times 1 cubed is just 1/3 minus 1. And then if we simplify this, I'm not going to do all the simplifications here, right? This is just, this is not even algebra. This is arithmetic, essentially, right? So we want to recognize how to simplify this. So I would encourage you to go ahead and attempt that, and you should find this. This is 9 times the square root of 2 plus 2. I believe that's what you should find. But notice here, we didn't have to substitute back. The substitution back wasn't required because it was a definite integral. Now, if you were to find the indefinite integral and then rewrite in terms of x, right? So remove the integration bounds. I know that this is a technique that we use, or that you use. I've used it too. Find the indefinite integral and then skip to the end and say, all right, now I'll put my integration bounds back on once it's in terms of x. And that would be fine, but that would also require that you write it back in terms of x. So there's different ways that you can go about it, and whatever you're comfortable with is absolutely fine. But that's all I wanted to cover for this section. So I'll see you guys a little bit later, probably back here in the office for some of section 9.4. You guys have a good one.